Okay, let us continue. Here, I think that one of the best ways to understand this idea of the demarcation criterion is really having in mind this non-falsifiable hypothesis the university is governed by love and hate, and seeing that this is a hypothesis that cannot be refuted by any empirical data. Now, you can describe that in the following way: whatever happens empirically, whatever you can observe, right, whatever are data, experiments, whatever, it can be subsumed under this hypothesis, this one, right? You can describe everything, I believe, in terms of a mixture of love and hate, metaphorically. I mean, it's not real love, but whatever that is, but certainly it's difficult, right? What real love is, it's also a difficult question, but also metaphorically it's quite a difficult question, what's going on here. And therefore, the hypothesis cannot be empirically refuted, right? Refuted by means of data, by saying, look, here's the hypothesis, here are the data, and the data tell us this hypothesis is false. That cannot happen with that hypothesis, and therefore deductivism says this is not a scientific hypothesis. Right? That's the story. And that may sound trivial to you, or may not perhaps, but it's very important to get that clear. If you discuss what science is, then you want to have a demarcation from pseudoscience, and from time to time that becomes very important. It is very important these days in the United States of America, where you know that there's a discussion about so-called creation science. You know, that are people who probably now won the election, or some of them at least, that happened. I didn't look at the newspaper. It wasn't in the newspaper today in the morning, but there are some people, so-called right-wing people then, who do not believe in evolution, and in the United States it's a fair amount of the population, and they believe in a Christian sort of doctrine of creation, and they say, no, creation, the story in the Bible is as good as the scientific story of evolutionary theory. There's always, when I give talks on these subjects in the United States, then it's necessarily in the discussion people ask me, how about the demarcation of pseudoscience from science, because we have this problem with creation science, right? And this creation science, I mean, it's just called science because these people who defend the creation of the living world by God, and of course the rest of the world as well, who defend that, they claim this is scientific, right? They claim it's scientific. Therefore, they say our children have to be taught both evolutionary theory and creation by God. And of course, every scientist says, that's not good, right? And therefore, we needed a criterion to show that an explanation of the diversity of life by an act of creation by God is not a scientific theory. It's just something else. It's not on the same level as evolutionary theory. It's just something else. Whether it's something good or something bad is a different story, but it's certainly not something on the level of science, and it should not pose as science. And, and claim, yes, this is also a respectable scientific theory. It is not. It's something else. It may be useful for your life, whatever, but it's certainly not a scientific hypothesis or scientific theory. And the point is then, for instance, how one could refute it is by saying, or how one could not accept it as science is, look, there are no empirical data that could show that it was not creation. Right? You can fit anything in this framework. Whereas you cannot fit everything in the framework of evolutionary theory. I mean, very simply, you can imagine immediately data that show you that evolutionary theory is false, right? Immediately. If you find in the Precambrian now bones of human beings, then it would be very difficult then, 2 billion years old or so, then evolutionary theory would be in great, great, great trouble. Okay. All right. That's the idea, and one more here that to get this in your mind, because that's important here. In other words, scientific hypotheses must be empirically risky, right? You're risking something in the sense that there is always a danger that by means of empirical evidence they are shown to be false. Once you have a scientific hypothesis, you always run the risk of being refuted by empirical data. Right? That's the point. And I added, which is not on the slides here, this little sentence here, they can collide with empirical data. Right? They can collide with empirical data. The hypothesis that the universe is governed by love and hate cannot collide with empirical data. You can have empirical data, whatever it is. You can imagine the craziest empirical data, and you can always say, it's a result of love and hate. Right? And real scientific hypotheses, they take this risk, right, of being in conflict with empirical data. All right, is that basic idea? Do I have more to say on that? Oh yes, I do have more to say on that. Oh, what a surprise. Good. I don't know where I am. Okay. All right, is that idea clear to you? Any questions concerning that idea? You may not see how important it is at this moment, but you must understand it. And of course, if you ask the question, what is the difference between, say, religion and science, and you may sometimes ask yourself that question, or you may be asked by others, you know, kids of sorts, your brother's kids or your own or whatever, people at home, and they may ask you, you know, what's different, science and religion? You should have some sort of answer, perhaps, right? If you are a scientist, perhaps you should have some answer. Anyway, and deductivism gives you that answer. Whether that answer is true in the end is a different story, of course, but that is the story that deductivism tells us about that. Now let's continue here. Now, this is an important consequence that sheds some light on the process of science. Contrast the following. Look back at inductivism. And for inductivism, the process of producing a general hypothesis is a rule-governed process. You know, there are rules to be obeyed, namely the three conditions, C1 to C3. Right? Observe as much as possible, nothing must be in contradiction to the observation, and vary the conditions. Right? So you have to obey certain rules, and only if you obey the rules you are allowed to articulate a general hypothesis. Right? Otherwise you are not allowed. It says yes, it's arbitrary, but if you follow the inductive procedure of generalizing in accordance with the rules, then you are allowed. Okay? So what I want to have here is only that the process of producing a hypothesis in inductivism is a rule-governed process. You are not completely free. You have to obey the rules. Like driving, right? You don't drive anywhere just anyhow. You have to, of course, you may go to Langenhagen or to the city center, but you have to obey the rules, right? Traffic lights. Red traffic light, you go through and say, I don't care, right? That's the normal procedure. All right. This was, again, a joke. Thank you. All right. Now, by contrast, for deductivism, the production of hypotheses is not constrained. Right? There's much, much less constraint as long as the resulting hypotheses are empirically falsifiable. Right? You may, in other words, in science, articulate rather wild hypotheses, while not usually during the master thesis. Okay? That's for the students. All right? But in general, people can come up with fairly wild hypotheses. The only condition, says deductivism, the only condition is that these hypotheses can collide with empirical data. Right? They must not be of the sort the universe is governed by love and hate. That's not allowed. But anything else is allowed. You are very, very free in science, according to deductivism, in the invention and formulation of hypotheses. Yes, you are fairly free. You are not restricted very strongly. The only thing is, it must be an empirical hypothesis, meaning, meaning what? Meaning the falsification of the microphone. Right? Let's see whether I can fix that. I can't look in the camera, unfortunately. There we go. This is an act. Yes, okay? Can you hear me? Good, thank you. That's service to the students. So you are, in deductivism, you are not much restrained in inventing hypotheses. The only thing is there must be empirical hypothesis, they must possibly collide with data. So Here's an example. You may know of benzene. That's a molecule that has the ring structure, you know, the 6 C atoms and then something else on it. And the idea that benzene has a ring structure was published and discovered and published in 1865. So it's a rather old part of organic chemistry, but it was a sensation because it was the first molecule discovered that has a ring structure, and people never before thought of molecular structure as ring structure. Now, the standard story how Kekulé came up with that idea is the following. Kekulé was a well-known, famous, successful organic chemist, and he already had dealt with many molecular structures, and his research project was the question of what the molecular structure of benzene is. And he had no idea. They simply had some empirical data about it, but they didn't really know what the structure is. Now, the story that has been told many times is this, that one day Kekulé went home thinking about the structure of benzene, and he sat in front of his fireplace because he was a famous German professor. He had a house and a fireplace, right? That was the 19th century. That has changed a little in the meantime. And anyway, in the 19th century, as a successful chemistry professor, you did have a large house usually, and you had a fireplace if you were in the north, right? So 19th century was, in some respects, a good century for scientists. Okay, now he sat there in front of his fireplace, and as he was already an older gentleman, right? Older gentlemen tend to fall asleep in the afternoon, sometimes, as I know. And he was somewhat falling asleep and dreaming about his molecule, right? And then he had the idea that these molecules, the C's, you know, they were like little snakes and they were dancing around in front of his eye. He was partly a little asleep, and then somehow they were dancing around and then they formed a ring, right? They were done, you know, the snakes had little one to this one and that one to the next one, and they formed the ring. And that was, you know, during half asleep and dreaming and so on. So that was the origin of the idea of the hypothesis that benzene has a molecular ring structure. You see, there is no empirical generalization from data. How he came up with that? Nothing, you know, zero, nothing. There is no control, you know, be careful in your observations. Nothing, he was half asleep, okay? He was half dreaming, you know? But the point is, of course, this was an extremely valuable hypothesis. And that was the genesis of this hypothesis. And you see, the genesis of this ring structure of benzene is not something that fits the inductivist story, because there is no inductive generalization. And you cannot directly observe it. You could at that time not directly observe the ring structure of that molecule. That was impossible. You couldn't take a microscope and look at it, right? It was a theoretical postulate, and then you had to find out whether the theoretical postulate is right or wrong. So the genesis of that benzene structure was a fairly uncontrolled, not a rational process. The man was half asleep, you know, and dreaming in front of a fireplace. No rational process. But of course, something like that must be allowed in science. Of course, because in the end, nobody cares about the way how Kekulé dreamt up this hypothesis. In that case, it's really dreamt up, you know, coming to his mind. Nobody cares. The question that people care about is, can you test this hypothesis? Can you present empirical data that show us then that the hypothesis is right? Why is it more plausible that benzene has a ring structure than being a linear structure like all the other molecules one knew in organic and inorganic chemistry? So he had to produce data, and that is what happened next. He went to the lab the next day, and then he or his assistants or who else, I mean, people at that time also had assistants in larger numbers in chemistry, and they did much of the work, of course, in chemistry, and some of you are familiar with these facts. They have remained the same, more or less, in academia. And then people were trying to devise tests and find out how could we test whether benzene indeed has a ring structure or doesn't have a ring structure. And that is what people were doing. So the process, how this hypothesis was formed, invented, was completely uncontrolled, but nobody cares whether it's controlled or not, right? The question is only if it's an hypothesis that can be tested, and the answer is yes, it can be tested, because I don't know in that particular case what the empirical differences are between the ring structure and the linear structure. Probably it's a question of energy. You can check some energies, or you can do X-ray refraction. Well, he couldn't do X-ray refraction because X-rays were only discovered 35 years later, so he had to rely on other things. I don't know exactly what the chemistry there is, but the point is that people then started thinking about empirical tests, right? So the genesis of the hypothesis is irrelevant. What is relevant is once you have the hypothesis, and of course it's an extremely risky hypothesis. I mean, Kekulé dreaming it up half asleep is no guarantee that the hypothesis is right. Of course not. And of course he knew it himself. He just said, bingo, that's an interesting hypothesis, let's test it, right? The genesis of the hypothesis is irrelevant. What is relevant then is testing it, having the hypothesis and then testing and then making empirical tests that look whether the data confirm or disconfirm the hypothesis. That's the idea. And as he was able then to devise tests, empirical tests, namely data that could eliminate this ring structure hypothesis, that could be in disagreement with it, therefore it's falsifiable. But the fact was that he produced data, and his lab produced data, and then later more people produced data that showed, well, that hypothesis is not in collision with the empirical data, just the opposite. The other hypothesis, that it's a linear structure, that this hypothesis collides with empirical data and is therefore falsified, it's wrong, whereas this one here survived. So this is an example, and that shows you also, again, in the contrast of inductivism and deductivism, that inductivism describes science as something which is, so to speak, a mechanical enterprise, right? There is no much freedom, there is no much creativity. You simply have observed your facts, theory free, and blah, and this one, and this one, and this one, and then you obey the rules, and then you generalize, and here you are with your hypothesis. It's not very exciting, right? But sitting in front as a rich man of your fireplace is very exciting, right? And then dreaming up a good hypothesis is even more exciting. And then getting it right is most exciting in science. When people think, damn it, Kekulé found it out, That's a revolution in organic chemistry. Wow, there are molecules that have a ring structure. Unbelievable. Wow, Kekulé found it out. That's great, right? And there's much freedom and creativity. So what you see here is that the description of, the general description of, so to speak, the character of science as a creative enterprise is much better in deductivism. In deductivism, it's described really as a very creative enterprise because you are so free how to come up with hypotheses. You may dream them up, you may observe thousands and millions of data and then sucking them a good hypothesis out of them, or whatever it is, right? Everything is legitimate there, as long as the hypothesis is falsifiable. The step then, that's the step we discuss next then, is of course the empirical tests. How to do that, that's of course absolutely essential, because otherwise all nonsense will populate science, and we don't want to have nonsense, we want to have good hypotheses, that explain something, predict something, are technically applicable. But the process of reaching the hypothesis is now a process that is not rule-governed. The only rule is the hypothesis must be able to conflict with empirical data. And that is a hypothesis. The ring structure of benzene is an hypothesis that can conflict with empirical data. And the story is that these were the weeks after this dreaming up the hypothesis that were filled with empirical tests of this hypothesis. Okay. Yes, as legend has it, Kekulé came up with the idea of this structure in a dream of snakes. Each of the snake bit into the tail of another snake. As a result, the snakes depicted a cyclic structure. That is the story. Okay. So this is a nice example. Whether it's literally really true is a different story. It's not quite clear. I mean, there are many things in science about the history of science, especially the big discoveries or so, when 30 years later then people describe how they came up with the discoveries. It has been shown that very often the stories are a little more legends than literal truth, right? That is because thinking back then to the situation is sometimes very difficult. And well, that's a longer story in the history of science. That's not our concern here. I'm just warning you in general, don't believe just everything that's told about the history of science, because if one really does very careful research, then it has turned out more often than once that the stories you are usually told in the textbooks about the history of science are not quite literally true. They are not lies, but they are not completely literally true in some cases. Okay, that's of no concern for you. You're interested whether you can work with the hypothesis or not. And here you certainly, some of you have at least implicitly used the fact, the apparent fact that the structure of benzene is a ring structure. Okay? That is what I said already a couple of times. Whether the hypotheses are then temporarily accepted in science, however, will be determined by the testing procedures. You know, there's a difference between something letting it in for the discussion in science, you know, and that is also, are you hypothesis in principle falsifiable? Then I'm willing to discuss you, right? So scientists were willing to discuss the ring structure of benzene hypothesis because they knew that can be scientifically tested. Therefore, they were willing to discuss it. They didn't know whether it was true or not. But they said, okay, that's a hypothesis we can test, right? If Kekulé had come up with the idea that the structure of benzene is governed by love and hate, right? Chemists would have said, what? Kekulé? Go to the hospital, right? You're out of your mind, right? That's not a notion of chemistry, love and hate. Forget it, right? But saying it's a ring structure, people said, wow, that's very strange. I mean, I don't believe it, but let's go to the tests. Let's go to the lab. Let's make tests and find out, right? And then in the end, of course, it can be a victory or a defeat for Kekulé, and it turned out it was a victory for him. So whether hypotheses are accepted in science will be determined then by testing procedures. You know, you are allowed in, yeah, but you may be kicked out very quickly again if the tests then show that it's false. Right? Okay. Now, the problem that is now waiting for us in the development, after we know in principle what the basic idea is of deductivism, is to describe in more detail the testing procedure, because all the weight regarding the reliability and the quality, the good quality of scientific knowledge, is now sitting on the testing procedure. Right? We have all the freedom to invent hypotheses as long as they are empirically falsifiable, according to deductivism. Right? We have all the freedom. But we can admit a lot of nonsense, well, crap, false stuff. Well, not really nonsense, but false stuff. So the weight is now, for deductivism, to have rather rigorous testing hypotheses in order to eliminate those hypotheses that are empirically false. Right? That's now the way. That was different in inductivism. In inductivism, already you have a strong filter already in the genesis of the hypothesis, because he said observe your data and then generalize from there and do that in a careful way, right? So all the nonsense was already eliminated at that stage. In deductivism, the nonsense will be eliminated at a different stage, because first of all, you are allowed to articulate hypotheses even if you have no empirical data for them. I mean, Kekulé had no empirical data for the ring structure when he came up with the idea. You know, there were no empirical data. They measured the chemical properties of benzene and everything, and they just didn't know the structure, right? But there were no data for the ring structure, and he just dreamed it up, said, could be a ring structure, why not? And then people started testing. And therefore, because you are so free to come up with ideas, the testing procedures must be very rigorous, otherwise you would keep all the false stuff, right? And therefore now all the weight in making this position of deductivism plausible as a theory of science is of course now in the so-called deductive hypothesis testing, and you don't know yet why it's called deductive hypothesis testing, But you know, so to speak, the strategic place of hypothesis testing, which is now here because we have the door wide open, not for everything, but for everything that's testable, and then we must eliminate that stuff that doesn't survive the testing. And therefore the testing must be as rigorous as possible in order to push out again from science all those hypotheses that are in conflict with the empirical data. And we must now have a look how that works in this image of science that deductivism presents. But I want to give you the occasion again to ask questions in case something is not clear, the direction is not okay. Clear. Is my speed okay? Am I too slow? Shall I go a little faster? Double speed? Triple speed? No? Okay.
I just have one question. What are the empirical circumstances imaginable to refute this theory that the benzene is circular?
Well, I don't know exactly how they tested it, but I guess it's probably the energy content is different, because in the linear case you have one less bonding than in the other case, right? And you may have optical data. If you do X-ray refraction, I guess it's very different whether you have this one or whether you have the ring structure. I'm not an organic chemist, therefore I don't know it, but in principle, I guess if you do X-ray spectroscopy, you see immediately whether a molecule has a ring structure or doesn't have a ring structure. Does anyone know enough chemistry to know that? How you test on the cyclic structure of molecules? I don't know. There must be empirical differences. I mean, the energy content is quite clear, that once you have the ring, you've got the binding energy, right, when you close it, and when it's open, there's no binding energy, so there's an energy difference, right? I know it not about this particular case, but the testing about the double helix structure of DNA, there it was done in a lab in London, not in Cambridge. There was a woman called, I think, Franklin, who didn't share then the Nobel Prize, which was probably a little unjust or quite unjust, whatever. And she had X-ray refraction data. So what you do is you have the DNA, you crystallize it, and then you do X-ray refraction. And then you get a pattern. If you're not a specialist, you don't see anything in the pattern, but you just get a pattern from the diffraction of the X-rays. And then you cannot read off from the pattern itself the structure unless you are really very experienced. Once you know, well, the pattern for a single helix looks like that, a pattern for a double helix looks like that, the alternative was a triple helix. And then you know these data, or you may know the data if you don't have a helix at all, but you have a linear thing, and then you see it on the data. So the point is, I guess, as I said, I don't know the particular case, there must be tons of possibilities how you distinguish empirically between the ring structure and the linear structure. How it was done in this particular case, I simply don't know.
My question was more that is it not the same procedure to demonstrate that it's valid, or to find that there's
a ring structure? Yes, same procedure, but different outcomes. I mean, if it's, for instance, a question of the energy and you can somehow measure the energy, then you get, in the case of the binding structure, of the ring structure, different energy than from the linear structure, and then you measure it, and then you get the energy, and that decides the matter, right? The procedure may be, yeah, you are right, I see your point. The procedure to find out whether it's a ring or linear may be exactly the same, but the result of the procedure is a difference then, right? Depending on the energy value you're getting, right? You see the point? The procedure, when you say, okay, these are my hypotheses, it's a linear thing or it's a ring, and then, for instance, you can measure somehow the energy of the molecule, and then you measure simply and then the result tells you, say the difference is 5%, and you can measure to 1%, then you can say, well, with high confidence I can say it's this structure and not that one, okay? Yeah. But the point is, whatever it is, you must have some sort of procedure to distinguish, and the data will be different. And of course you must know enough chemistry to know how you can see the difference between the ring and the linear structure in certain empirical data. And that may be an energy measurement, that may be X-ray diffraction, which was certainly not the case at that time, or any optical, I don't know, I simply don't know enough chemistry about this period of time. But you must then think of an idea of data that distinguish between the two hypotheses. And that is what happened. And people, of course, said immediately at that time, in principle, we can find data, right, in order to decide that question. And of course, every chemist says, yes, if there is a difference in the structure, somehow it must be possible to find data that decide the question. Whereas in the case of universe in love and hate, think about data that can decide the question whether that's right or not. You can't find any, that's the point, right? Whereas in the chemistry case, you can find data, and as I said, I don't know exactly, I can have a look, possibly I can find it out, what the procedure was at that time, what sort of techniques organic chemistry had in order to decide this question. I simply don't know it now. All right, is that clear enough? All right. Okay, any other questions? Okay. Now, what may be very surprising at first sight, at least, is the sentence that is now on the screen, namely, the main tool for empirical tests of scientific hypotheses is logical deduction. Say, what? Logical deduction? That's incredible. But that is the case, and that is the case that deductivism defends, and I'm going to try to show you why this is fairly plausible. Logical deduction is the same thing that you know from mathematics, right? Deducing something, making logical consequences. And I show you how that works. Now, the general idea of this testing of hypotheses is this. From the general hypothesis, you deduce specific sentences that can be compared with empirical data. Okay? Let's take up the example again. Let's say we can measure some sort of energy in order to deduce, or in order to show whether benzene has a ring structure or a linear structure. The idea is that from the general hypothesis it has a ring structure, you can deduce certain consequences about its energy, right? Or from the hypothesis it's a linear structure, you can deduce certain consequences about its energy. And then you measure the energy, right? And then you can distinguish which data are consistent with the hypothesis and which data are not. That's the idea, right? So you start with the hypothesis of which you don't know whether it's true or not, whether it's acceptable or not. And you deduce something from it, you suck something out of it, of its content, something that can be measured, for instance, energy or diffraction data or whatever it is, and then you measure them, and then you get an argument for or against the hypothesis. That's the general idea. From the general hypothesis, you are trying to test, specific sentences are deduced, for instance, about energy content, that can be compared with empirical data. That's the general idea. You start with it and pull something out of it that can be compared with empirical data. So here's a different example. It's a very simple one. It's Ohm's law. Okay? That's relevant for everyone in science, I guess, more or less. Ohm's law, the resistance of a certain current is the voltage divided by the current. Okay? That's probably familiar to everyone. I hope so, at least. Now, this is a very simple law, but it's, of course, extremely important because it holds over large areas, many materials, and a large domain of currents. Not everywhere. If the current is too strong, of course, the thing will simply melt, and then the current is over. At any rate, but as long as the current is okay, then for many substances it holds nicely. So for a specific piece of matter, imagine you have a specific piece of matter and you want to test Ohm's law, then by simple mathematical manipulation, the following equation can be deduced, and that is not very difficult to obtain, right? You take a specific current and a specific voltage and put it in here, and then you take another specific current and a specific voltage, you put it in here, and both are equal to R. So the ratio between voltage and current is constant for this particular piece of matter, that has this particular thing. So, and then you can of course have a U3 and a I3 and so on and so forth, and this can be tested because you simply measure these, right? You have your piece there, then you take a battery, and then you measure the voltage, and you measure the current, and then you change your battery and take a higher current, a higher voltage, and then you get a higher current, and so on and so forth. And you do that for many cases, and you can measure that, right? And the prediction of Ohm's law is that this ratio is a constant, right? And that you can measure. And then you simply measure it, and then it turns out either that yes, these data, it is right that this holds empirically, namely then Ohm's law is confirmed, or it turns out that it is not confirmed, right? So the point is, that's exactly what I said here. From the general hypothesis, that's this one, specific sentences are deduced. These ones, they are deduced here, mathematical operation, that can be compared with empirical data. Yes, that's the case, because I can measure voltages and I can measure currents, right? And then I can measure that and look whether Ohm's law is in accordance with the data or whether it is not in accordance with the data. And that is what I just said. The equation can be, this equation can be compared with the results of measurements, right? That's the idea. And then, of course, you have at the same time, once you know what the ratio is, you have measured the resistance of that piece of matter, right? That's the basic idea. Once you know that law, then you can, of course, build resistances and use it for technical applications, okay? Now, if the measurement, now this is rather trivial for every natural scientist, of course, if the measurements differ significantly from the deduced values are these values, right? If that is the law, then these are the deduced values, that the ratio is constant. And if the ratio is in your measurement not constant, significantly not constant, then the hypothesis failed the test, right? And that can happen if you take the temperature. If you take a too high temperature, then Ohm's law doesn't hold any longer. And then you show, well, Ohm's law does not hold for too high temperatures, say in the case of copper or whatever it is, right? And it's falsified, and then it is falsified. It's shown to be false for these particular cases, and otherwise it survives the test. It survived the test, and you can say, yes, in this particular temperature range and this particular range of voltages, Ohm's law holds because I have tested it. So that's the idea. You don't see any sort of inductivism here, you know, going up to the data, going up from data to generalize. No, doesn't look like it, at least. There's no generalization. But what you do is you start with the hypothesis, you deduce something from the hypothesis that can be measured, then you measure it and look what's the relationship between the deduced stuff and the measured stuff. If there's a discrepancy, you say, wow, that doesn't look good for the hypothesis. Or there's no discrepancy, then you have a test and the hypothesis survived the test. Okay, let us stop here. I have to say more about that, but that will have to wait for 1 week. And I wish you a wonderful 7 days until I see you again next Wednesday.